This video is going to talk about non-parametric tests that can be used to test hypotheses about a single proportion. These are alternatives to the z-test for when conditions are not met. Remember that the conditions needed to use a z-test to test hypotheses about a single proportion are that we need to have independence between the observations and that we need to have a large enough sample size so that both n times p and n times 1 minus p are at least 10. So if the sample size is too small, we don't want to have to just throw up our hands and walk away. We want to be able to do something. So what are some options that we could use instead? One is that we can use what's called an exact test. And the other is that we'll be able to use a test based on simulation, and we'll look at how we do both of those things in this video. We're going to use an example. 12 infants were enrolled in a study. Each infant was shown a puppet show in which there were two characters, one who was a helper and the other who was a hinderer. After watching the puppet show, each infant was presented with the two puppets and chose between them. 10 out of 12 infants selected the helper puppet. So what we want to know is how strong is the evidence that infants prefer the helper. Our null hypothesis here is going to be that the proportion of infants who prefer the helper is equal to 0.5. What that would mean is that there's a 50% chance of choosing either puppet and that the infants have no preference between the two puppets. The alternative is going to be p, the proportion of infants who choose the helper, is greater than 0.5. So this would indicate that infants are more likely to prefer the helper. And keep in mind, we know that in the sample, more than half of infants selected the helper. What we're really thinking about sort of is, okay, well, this was a sample of infants, but among all infants, are they more likely to prefer the helper? That's what we're trying to decide. So an exact test in this situation would use the binomial distribution to find the p-value. We aren't going to be able to use the z distribution because n times p and n times 1 minus p are both less than 10. So when we do the exact test, we say, okay, well, let's let x equal the number of the infants among the 12 that were randomly selected who prefer the helper. If the null hypothesis is true and each child is equally likely to prefer the helper or the hinderer, then this number who chose the helper would have a binomial distribution with n equals 12 and p equals 0.5. Since the p-value is the chance of seeing our observed sample result, that was 10 choosing the helper, or something more supporting the alternative, something larger than that, if the null hypothesis is true, we can use the binomial distribution to find this p-value. So the p-value is equal to the probability that my binomial random variable here takes a value greater than or equal to 10, and I can find that using the formula to calculate probabilities that x equals 10 plus the probability that x equals 11 plus the probability that x equals 12, and it gives me a p-value of 0.019. Testing at the 5% level of significance, this would be small enough to reject the null hypothesis, and there is evidence that infants prefer the helper over the hinderer. If I'm going to do this test based on simulation instead, what I'm going to do is I'm going to simulate a distribution of results that might occur due to chance if the null hypothesis were true. Now, if the null hypothesis were true, then if I consider 0 being choosing the hinderer and 1 being choosing the helper, then basically I'd have a situation where each child was equally likely to choose both. So what I'm doing here is I am creating a place to hold the result, so I call that result. I'm going to do 1,000 trials, so I made it 1,000 spots long. I set my sample size. I know there were 12 infants, so n equals 12. And then I'm using a for loop. Now, every time that I run through this for loop, what I'm going to do is I'm going to take a sample of 12 from the values 0 and 1. And I'm considering 0 to be choosing the hinderer and 1 to be choosing the helper. And I say replace equals true because every time I come through and make a choice for my sample of 12, I want there to be an equal chance of choosing both of those. Then what I'm going to do is I'm going to add up, so sum the trial. So keep in mind I'm going to have zeros and ones in trial. And if I sum trial, what it's going to do is it's going to count up the number of ones. That's counting the helpers. Then I divide by n, the number of children. And so it's going to give me a sample proportion for that trial. And I'm going to put that into the ith spot in this result vector. And so what this is doing is it's essentially doing 1,000 different simulations of choosing a random sample of 12 with a 50% chance of choosing the helper and figuring out what the sample proportion was. And so I made a histogram of the results, and we can see it's centered very close to 0.5 because that's our null hypothesis. And as I'm thinking about finding my p-value, 8 out of 12 is out here. I'm going to be thinking about, okay, what's the proportion of results that are out in this tail? And so again, when I want to find the p-value is going to be the proportion of the simulated results that are at the sample result or even more extreme. So the way that I can find that is I can say, okay, I'm going to check each spot in results to see if it's greater than or equal to 10 out of 12. I'm going to add up that vector that was checking so that I know how many of them were greater than or equal to 10 over 12. Then I'm going to divide that by the total number of simulated samples, 1,000, and it's giving me the proportion of results that were as extreme or more extreme, which came out to 0.018. So this is an alternative way to estimate the p-value in this situation. It's not exactly the same as the 0.019 that we got using the exact test, but it's very similar. So these are two ways that we could come to a p-value in a situation where our sample size is too small to use the z distribution to test hypotheses about a single proportion. Thanks.